So this is going to be a little bit more technical, so I hope I'm not going to go too far towards computer science, but you know, I mean, ask me questions or tell me, we'll see what we can do. A little bit about myself, so I'm Grzegorz Gawron, I'm heading a team at VirtusLab from Krakow, a team of software engineers, mostly. We do have some data engineers as well, but essentially what we focus on is building big data systems, mostly for big customers, and most of the examples that I'm going to be talking today about are about one of the biggest retailers in the world. Actually, I cannot name them, but this is what we do. So we are used to working on big data clusters, Hadoop clusters with tens of thousands of cores, hundreds of terabytes of RAM, and some petabytes of HDFS storage. Right, so most interesting examples, and we're going to be talking about those today as well, is about optimization that is happening in retail. So when I first started looking at this, I was really surprised how much thought goes into optimization. Various processes, is like hundreds of processes that happen in a big retail organization. So big retail organization, I mean organization with thousands of stores in various countries. So there is a lot of that, but we're going to get to that soon. And VirtusLab is a company that specializes in software engineering, so we have about 100 software engineers above that now. We do some R&D as well, certified trainings, a little bit of ad here, but okay, so retailing challenge. So what is the optimization challenge in retail? So that's going to be a little bit of introduction for those of you who know retail from shopping experience, but not from, you know, behind how it actually works. And we're going to have two cases. One is a case of Apache Spark as a tool being used as sort of generic compute engine. We're going to get to that, and then there's going to be sales forecasting. So those two cases are the cases where we were able to actually help the customer a lot in what they were doing. So I think that's going to be pretty interesting for you as well. I already mentioned it's about the real case. Right, so what is the challenge? Oh, too far. Okay, so what happens is you have on the left, you have something that produces goods. The goods get to the warehouse. From the warehouse, the goods go to the store. Then there are some vans that actually, if you buy things online, it can be delivered to you, right? So where is the optimization in all this? So here are a few cases. So for instance, let's say you have a fleet of vans that is to carry out the goods to the customers. So let's say customers order stuff online, and you have, let's say, I don't know, 100 vans for the warehouse to distribute those goods. The question then is, okay, so how do we make sure that we always deliver on time, right? So you cannot assign more deliveries to a time slot that you have vans able to actually distribute those, right? But to be able to say that, okay, I know that I have the exact number of vans for the orders, there is a lot that you have to maybe predict first of all. So for instance, you need to assume certain things about the traffic. So, okay, I'm gonna, I don't know, there is a time slot for 9 a.m. in this area, you know, the travel times are actually longer, so the van is not gonna get there on time. So I will be able to distribute less of those goods on that time slot. On the other hand, you know, if you want to distribute something in the middle of the day, maybe it's better. Right, so there's various considerations there. Obviously, one of the things that you can do as well is you can put prices on the time slots, because how do you actually? So if there is a person and they say, okay, yeah, I want because usually people do want to get stuff delivered when they are after work, maybe 6 p.m. So how do you make sure that those time slots that are very popular, people, not everyone just goes for them. Well, you just raise the price of that time slot, right? But how much do you raise that price? And this is another question that can be answered via some optimization methods. So you try to predict how many people want to deliver that on a certain spot. You make the price a little bit higher. Ideally, you would like people to order delivery time slots so that your vans are fully utilized all of the time, so that you don't have, like, in the middle of the day there is nothing to do, but then at the end of the day everyone wants to get stuff delivered. So that's an example of this optimization. Another example that I wanted to mention is about the warehouses, for instance. So let's say you do have a warehouse, and again, we're talking about the same order. So you order something online, it needs to be packed, right? So someone or some automatic system needs to go through the warehouse and actually pick the stuff that you ordered, right? Now, how long is it going to take? Let's say you have thousands of those orders and they need to be picked. And let's say you do not have automated warehouse, not all of them are. So you need to somehow predict how much it's going to take you to actually pack those items, so that you can let people know when they can expect their goods to be delivered. And this is yet another thing where you need to predict some stuff. So maybe you can also optimize the warehouse, because if you see certain trends or patterns in what people order, maybe you can move products in the warehouse so that the most often bought items are at the entry, right? So when people start with them, they don't have to go far to actually pick those. By the way, I was mentioning those automated warehouses and manually picking things. This is pretty interesting, and I didn't know that before, so probably you don't know either. So when you do not have an automated warehouse, the way the order is picked, you would have this special trolley with like maybe 6 compartments, one for each order. You would have those lists of shopping, and you would have the route in the store planned. So where you need to go, which items you need to put into each of those compartments on your trolley. And then you come back, and here's the 6 deliveries ready for the people, right? So this is this manual thing. So if you want to optimize the time of those people that actually go and pick up stuff, there is a lot you can do with the data, essentially. So again, as I was saying, you can move reorganize the warehouse so that it's quicker. You can also make decisions about, okay, so how many people we actually need on the floor to go and pick those things up. Because let's say at midnight we know how many orders we need to deliver the next day, and then sometimes you might want to, I don't know, employ some more people. Well, not employ, I guess the contracts would be that you just call for more people or less people. And again, that's another optimization for you. So here's just 2 examples of deliveries and warehouse organization. That you can see that there is a lot of optimization that can happen, and indeed happens behind the scenes. Okay, so a little bit of an abstraction of how it would work. So if you have lots of data, you are able to predict certain things. Like for instance, here's a few examples. There is this trolley picking your orders in the warehouse. So there is some trolley routes history. We know what sort of routes the trolleys made through the store. You can predict, for instance, a congestion in various parts of the warehouse. So for instance, there is always like a queue of trolleys waiting at this spot, maybe because the products are very often bought and there is too little space for people to actually go in there and pick those things and they have to queue up, for instance, or maybe a corridor between the shelves is just not wide enough in this location. So it sort of predicts the congestion, and that lets you optimize the layout of the store. So you might want to make this corridor wider, for instance, at this spot, or maybe just put the products more widely in a way so that more trolleys can have access to those. So you would predict the congestion by changing the layout of the warehouse. You could optimize this picking time that you're after, right? Because you want to have the time that the person picks a given order as minimal as possible so that they can maximize their time on the floor, essentially. So like in a graphical form, it would be, there is some optimization function. You move this thing on the horizontal axis. You change that and you optimize the thing that you want. And there is various other examples. Let me not go through all of those now. We can get back to that if we still have some time later. Okay, so what is the business value of computer science in all this, right? So you have, what is computer science? From my perspective, a lot of that is about optimizing algorithms that you have. So you might optimize the time complexity of an algorithm. You had an example of this n log n thing at the very first page. You might leave the time complexity the same, but you might want to parallelize that algorithm, right? So that if you have 100 machines, it's actually going to run much faster, right? So, and to be honest, quite a lot of those problems that we see, especially at the initial stages of optimization, is very nicely improved with just parallelizing the algorithm in the right way. And quite a lot of improvement in the systems comes from that. Now, so what happens when you improve an algorithm? Then the prediction we were talking about, this prediction of congestion, for instance, in the store, can be more precise or faster. About the speed, they can be really dramatic improvements. I mean, what we've seen is things that initially were planned to run for, day or days, we were able to bring down with just the parallelization to minutes. So it's really, it's a real difference also in how people approach this thing, because if you know that something is going to take a day to calculate, then you plan for it differently. So for instance, in this case, they were, the customers were planning to, okay, so we're going to do like once a month, we're going to do a full recalc, which is going to take 2 days. And 3 times a month, we're going to do just a small recalc, which is not going to be, let's say, as precise, but it's going to take, just half a day or something like this. So they were forced into planning things like that. But once you bring it down to 10 minutes, you don't think about it. You just calculate it every day and that's it. It's not a problem, right? So here is this gain from actually having a bigger thing. But in any case, so once you have this more precise and more frequent prediction, you can, for instance, translate that into a little bit better optimization, and even 1% optimization depending on the size of your organization, right? So here a trolley would represent 1 store. So if you have a retail chain with loads of stores, like thousands, then every little optimization, if applied to all of those stores, actually matters a lot. So it might turn out that 1% optimization improvement is going to be, I don't know, millions in budget for the optimization team, right? Because just gained by optimizing this. So, this is really the business case, right? So if you optimize it a little bit in a big organization, you actually gain a lot of money. So that's the whole thing. Okay, so let's get down to the first specific example. How much time do we have, by the way? I don't have a, what's the time? 36, okay. So that's all right, we still have quite some time. Right, so what is the business case here? So business case is, it was actually a sales forecast that the company was doing with a MATLAB simulation model. So they were running that in MATLAB. That was a single box, a big model. So as you can see, this is like big fat calculation that was happened for quite some time. I mean, it was one single piece of that calculation happened for 3 hours. So that was just, I mean, it wasn't too good for them because they did want to do more of those. So that's why they started talking to us about improving this. So, but you know, the thing is really simple. So you have some data, you have some simulation algorithms that run in MATLAB, and then as a result you get sales forecast. But to be honest, in this particular case, it doesn't matter really that much. You know, what the data was, what the results was. It's really this 3 Ps, right? You have some data, you have some computation, and you want to produce some results. I just want to focus on this very generic idea. So one of the things they did was, okay, so if MATLAB, you know, we cannot distribute that calculation with MATLAB too well, why not rewrite that in Python? And well, if we distribute it better, in Python, then it's going to be great because it's going to be quicker. But unfortunately, you know, just this rewriting that to Python shows that MATLAB was pretty well optimized in terms of what it was doing, because the runtime here got actually 10 times, I think, yeah, 10 times slower, more or less. Okay, but that is a good first step. But you know, if we have it in Python, we can actually, we have control over how we split it into little parts, and we can then run each of those little Python parts on one machine. If we have loads of those machines, then, well, it's going to be faster, right? But the question for them was, okay, so how do we actually parallelize that? These were data science guys writing MATLAB models, not really making sure that that runs on production. But what they had, right, what we have this big Hadoop cluster with, as I was saying, tens of thousands of cores. There is Apache Spark on that. So obviously we could try to write something that would be very optimal. But if we have something already that is working, let's see how it's going to perform, right? Maybe that's going to be enough. If it's enough, it's so much easier. You don't have to request for any new infrastructure, you just run on this. The only problem with that is that, just coming back here, Apache Spark, how many of you have used this? Maybe hands up, quite a few. To cut the long story short, Apache Spark is designed to work with huge amounts of data. So we're talking about like millions and billions of rows and transforming those somehow. Here we don't have this case, right? We'd be happy with maybe splitting that data set into 100 packages, right? Or maybe 1,000, right? But not millions or trillions. So Apache Spark is really optimized for, for those large data sets. That means that, okay, yeah, it can distribute smaller sets, but it might happen that it's not going to be very efficient. And let's see how it can actually be done. So if we treat this problem of ours as a very, as I say, generic compute engine, that is, you have some data, you have some logic, computation logic, and you want to get some results, Apache Spark, sorry for a little bit of maybe going too much into detail, but essentially this is a very simple thing of just mapping each of your inputs with a custom function of yours, which is your Python code that we were able to just extract out of MATLAB, right? So if you do that, and that's pretty simple to do, it's going to be great, right? Because as you can see, this little computation barrels are now much smaller, so they take less time. So if you just run all of them in parallel, if you have loads of cores on your cluster, it's going to be great because it's going to be 100 times faster, right? Okay, we might go back there. It's a little bit more theoretical, but yeah, let's focus on the actual little things that how we are going to get there and what problems we have if we try to do things like that. So first of all, we need to decide actually very, down to the earth problems. So so we have this MATLAB file. How will Spark be able to access that, right? There is several ways. Maybe there's no point to go too much into detail with them, but for those of you who know HDFS as a distributed file system, you can put those things on this distributed file system, and there is a hope that it's going to work much better with Spark this way. And this is the way we actually went. But here's the part that I wanted to get to really. So first thing, when you actually try to do this with Spark, with distributing the work over let's say 100 of those pieces, you're going to notice that Spark did this strange thing, right? So he took like one calculation here, but then took one execution engine and just queued up like 10 of those computations. So this is really not what you wanted, right? Because you wanted to run all of them in parallel. So so this is a problem of like using the tool that was not really supposed to do this, but on the other hand, it's available, right? So it has some advantages, some disadvantages. And by the way, I think this is a really, how to put that, that's a summary of a lot of interesting computer science problems. Like in the past, when you didn't have gigabytes of RAM in your machine, but you had like 64 kilobytes and you had to feed everything into that, you had to do a lot of thinking of how you do it. And this is a very similar thing, actually. We are like, I don't know, tens of years later, but still similar problems exist. You have something and you have to feed something else into it, even though maybe it's not exactly designed to do it. And we'll see actually it can be fit pretty well. So once you dig a little bit into the code, and you actually have to dig into the source of the Spark to see what happens, is that there is a special way that you can run a Spark job using the Spark context, which was actually sort of deprecated in the new version, but you can still use that. All you need to do, you need to just make sure that you use the right batch size. And that helps, right? So that actually distributes it over all of the machines that you have nicely and equally. But here you would notice another problem, right? So once you run this, you still see, okay, well, it took not like 100 times quicker on 100 jobs, because some of those jobs somehow were much longer, right? So the data that you had was skewed. So for some of those parts, it was much quicker to calculate than for the others. And obviously at this point, you might just think, okay, so what do I do? One thing is, you might try and combine those things. So let's say put this computation, the short computation at the end of the long computation, for instance, and then somehow make that equal. But I guess the best way, if you're actually in cooperation with the data scientists that design those models, is to just ask them, guys, here's the problem. How can we make it so that we don't have that data skew, right? And just go and change the model underneath a little bit for what it is. But this is what we've done, and we sort of improved it a little bit, but not to the full extent, because for an example of what happened here was that they said, okay, yeah, fine, because what we can do, we can make these packages independent by calculating like a sales forecast for each product independently, right? But each product is unique. That is, for one product, we might have quite a lot of inputs, history, and the sales forecast might be more precise because of that. For some other product, we have less history, right? And the one that we have less history for is just going to run quicker, I mean, there's not much we can do about that. So you can go to some extent in optimizing this, but at some point you need to accept that, yes, this is what it is. I mean, if you just want to parallelize this, this is what you're going to get. So that's what happened, but, and we said, okay, yeah, so that's probably the best we can do. But now you have another problem. Another problem is that once you run all this, you realize that, let's say, your whole job takes those 100 executors on your cluster. But okay, some of those jobs are quicker, so maybe we should release those executors, right? Once they calculated this first piece of work, you can just release those and use 99, right? And then off you go, and once you stop calculating the last one, you just have one executor reserved on the cluster, and the rest of the 99 of them can already do some other work, right? And obviously you have to think about that, but once you do, Spark has this dynamic allocation settings that you can use, and you can actually go and make it behave like this. So essentially you have executor reserved for just the duration of the calculation time, and that's what it is. So the final outcome, once we were able to do with this model, you remember we started with 3 hours for the model, and we actually ended up with 6 minutes for the model. Which is, you know, pretty large gain, given that we didn't really use the, you know, right tool for the job, but the tool that we had. And it, you know, it's a big gain. It's a big gain. They were pretty happy with that. So if you calculate that, that's about 30 times faster, if my maths is kind of okay. So to summarize, we start with this MATLAB model, and after some steps, we actually got to this distribution model that was able to produce the sales forecast much quicker. And by the way, the thing that I wanted to stress, this way of approaching problem is pretty generic. That is, with Apache Spark, you can really take any problem that can be cut into pieces and just do the same thing, right? It's not a problem. And it, yeah, gives you quite some results. Okay, another case I wanted to talk about is, again, this is sales forecasting, but you know, a completely different project by different people, done in a different way. They didn't use MATLAB for this. They sort of used Python straight away, but they based it on time series statistical packages, Python packages. But the problem was really the same. So they were able to run this forecast, and they were running that manually on their machines. And it was working, but you know, it took quite a lot of manual time to run that, both manual time and actually sort of elapsed time till you actually get the your sales forecast in the end. So they were thinking, okay, yeah, how, I mean, it's okay because we do the sales forecast for just this one, let's say, store, and it still takes a long time. How are we going to scale it up for thousands of stores that we have, and maybe even not thousands of stores, but for each store you would like to forecast each and every product in that store. So if you multiply this, you suddenly have thousands and thousands of little forecasts that you need to run. And currently we can just run one of them, and it takes us like the full day to run, right? So that's completely not scalable. So here is a similar problem. So yeah, a little look at what sales forecast would be. Let's say you have some time frame. Here is now. And here what you'd like to see, you know, after 2 weeks time on, yeah, actually there is some 50 here, but that's probably, yeah, so there's a few weeks, right? So there's weekends where you probably, the store was closed at those points. By the way, this data, it's not really that important for the presentation, but this is based on some of the Kaggle competitions, the Rossmann data, because I can't use the data from the actual project here. But anyhow, so the problem is you have some time frame in the future that you want to predict what your sales volume is going to be, right? So the blue bits is the real sales that will happen over those that period of time, and obviously we know that once we're here, right? Not in the future. But when we are at the 0 point, you don't know this blue line, so you try to sort of estimate this with this yellow line. So this is like particularly bad prediction in this case, but just to show you what you can start with. Okay, Coming back to our problem, we have thousands of stores, lots of products in a store. So if you multiply that, let's say you have thousands of models to calculate. But the good point about this is that each of those is actually, you can treat it as an independent piece of calculation. Again, the same thing as last time. You can actually, if you use your Spark, you can actually use, distribute those on multiple machines and run those. Now, I just wanted to go a little bit more into the details of Apache Spark. So again, if you're not a software engineer, sorry, that's going to be pretty brief. But essentially what happens is you have those worker nodes that can run your executors. So executor could take a few of those cores of your multiple thousand cores on your cluster. And each of those executors could run a task, and that task could be a set of your store product data. So if you do it that way, this is how it works underneath, essentially. A difference in this case here to the one that we talked about before is that over there we had this generic file on the input and something as the result on the output. Here we know exactly, we have the data in Spark that is good for what Spark does. So it is millions and millions of rows because all of the historical sales, for instance, of a given product, whereas on the 1st of January, that much was sold in this product, of the toothbrush in this store. And you have, if you multiply that by store, by dates, and by products, you have quite a lot of data. So here is a different usage for Spark when you actually go down into those loads of rows of the data. So essentially what I wanted to show here is after a lot of data munging, and we can probably go to that later, but what you want to do, and the big problem we had was that, this thing at the end is this time series Python library that data scientists used to run on their local machines, just clicking on command line and running those. With Spark, what you can do, you can actually take any Python library, any Python code, and just run it if you give it enough inputs. So the idea was, okay, so if we want to have a prediction for store and product, let's clean the data with Spark, which Spark is great for because it's going to distribute all of the cleaning across all your cluster. So you can clean the data, you can prepare it, you can prepare features, and then you can collapse all those features for one store and product into one row, and on that row, run your Python time series code. And this is exactly what happens. So again, you see this is this workaround, this connection to the normal Python machine is not really the design of Spark, but you can do that, right? And if you do that, you have some great results. So here is a little sort of architectural view of how it works, because Spark, if you have come across that, is based on Scala, a JVM language. So those bluish bits are JVM running machines. This is a cut across the nodes. Here you define what you want to compute in Python. Then it goes into this Spark engine running on JVM. And then once you actually go to running this custom Python library code on each executor, you actually start communicating with Python again. So JVM to Python communication. And then it goes back. And the results are saved down as a sales forecast in the end. So what are goods and bads of this? So the goods are obviously that if you're a data scientist and you were running your one model on your machine, you're going to be happy to hear that actually without many changes to your code, you can just run it for hundreds and thousands of those across the cluster. And that's great because you're still developing in the library, the Python library that you wanted to develop. and yet you have it fully productionized because it's just going to be kicked off in parallel on multiple boxes. So this is good news for Python. Not so good news is that, well, you know, these communication can be costly, right? So there is some, the data needs to be serialized, the Python process needs to be kicked off, data need to be communicated and so on and so forth. So it's not that efficient in a way. But then again, you know, I mean, this is the tool you have. This is the, you know, the efficiency you get is, gives you enough of benefit to actually use it, right? Without actually looking for some other tool. So just to summarize that, you don't need to look for anything else. Apache Spark is pretty standard on any cluster Hadoop installation, so you can just use it. It's fully productionized in a way that you can utilize 100% of your cluster if you want to. And obviously data scientists just keep the stuff that they want to keep. Communication is costly. Python is also not that scalable of a language. So yeah, you better stick to, at least that's what I, probably some people are going to jump now, I don't know. But you know, it's great for smaller scale scripts or models, that sort of thing. Okay, and that's it from me. Yeah, I'd be happy to take any questions if you have them. Or if not, you can reach me somewhere else. Yeah, there's a lot of other use cases that I can talk about. There is a question, okay.
Have you heard something about Python UDF, Pandas UDF, introduced in the recent version of PySpark? It is actually designed to fix the problem you described here, this slow communication between JVM and Python.
So we use, for this communication, we use the PySpark UDFs, right? You're talking about something else, I understand, right? Okay, yeah, so we, at the point that we were doing this, we didn't know about that. Is that something recent or? Okay, so that would be a nice way of actually improving this. Thanks for the hint, I'd have a look at that. Okay, I guess that's, oh no, here's the question, let me.
So, did you find out why, like in the first example that you gave, you said that MATLAB took you 3 hours, then Python 30 hours, like 10 times more, and it seems to be not something that it was because of Python did something, but it seems to be like more because there was something wrong with the implementation, like for the first thought would be, like, have you found out what was it?
Yeah, so actually at the first look at the Python code that was supposed to translate this MATLAB to Python, you know, I immediately was talking to the data scientist that, okay, well, the way, you know, you could do it, you could use, for instance, more vectorized operation in Python, and in that way actually run it under normal, you know, C++ or C code speed at the bottom. And obviously this is also on the plan to improve. What we were showing here that even if you didn't do those improvements, it actually behaved much, much quicker. So if we were able to optimize this Python code even more, well, or optimize this Python code, it would be much quicker. So the stuff that I was presenting here was without additional Python optimizations, just simple translation of the model. Okay, that's probably it. Yeah, so yeah, do feel free to grab me later on.